If you're here, you've probably already heard the whispers. An interstellar visitor, a comet unlike any ever recorded, has been racing through our solar system for weeks, and on December 15th, it will make its closest approach to Earth, closer than any confirmed interstellar object in human history. But here's what's really disturbing. The most critical 3 weeks of observation, the period when this object could reveal its true nature, will happen during an astronomical blackout window. Every major telescope, every space observatory, every watchful eye we've pointed at the cosmos will be completely blind to what happens next. How is that even possible? How could the most anomalous interstellar object ever detected vanish from every telescope's view at the exact moment we need to see it most? You might be thinking this is just another viral space story, another clickbait headline designed to get reactions. But what if I told you that NASA scientists, independent astronomers, and even researchers who've spent their entire careers studying comets are genuinely puzzled by this object's behaviour? What if I told you that the mathematical probability of 3I Atlas following its current trajectory grazing past multiple planets, exhibiting chemical signatures that don't match any natural comet, and timing its closest approach to Earth during a total observational void is so astronomically small that some experts refuse to even calculate it publicly? Let me be clear about something from the start. This isn't about fear. This isn't about doomsday predictions or alien invasions. This is about something far more unsettling, the realization that we might be witnessing an event so rare, so statistically improbable, that it challenges everything we thought we understood about how objects move through space. And the fact that it's happening during a window when we can't watch it? That's not just inconvenient. That's the kind of cosmic timing that makes even skeptical scientists pause and ask uncomfortable questions. 3I Atlas was never supposed to be remarkable. When interstellar objects enter our solar system, they typically follow predictable paths, hyperbolic trajectories that swing them around the sun and send them back into deep space. We've only confirmed a handful of these visitors in human history. Oumuamua in 2017 was the first, and it sparked years of debate because of its unusual acceleration and elongated shape. Then came Borisov in 2019, which behaved exactly like a normal comet should, predictable, explainable, boring in all the right ways. Scientists breathed a sigh of relief. The universe made sense again. But 3I Atlas? This thing is rewriting the playbook. From the moment detailed observations began, astronomers noticed discrepancies. The object's coma, the cloud of gas and dust that surrounds a comet's nucleus, wasn't behaving normally. The spectroscopic readings showed chemical compositions that didn't align with what we expect from objects formed in other star systems. And then there was the trajectory itself, a path so precise, so seemingly choreographed through gravitational assists from Jupiter, Saturn and Mars, that it raised eyebrows in observatories around the world. Here's where it gets deeply strange. Comets are dirty snowballs, chunks of ice and rock left over from the formation of solar systems. When they get close to the sun, they heat up, gases sublimate, tails form. It's a process we've observed thousands of times. But 3I Atlas is displaying outgassing patterns that some researchers describe as geometrically anomalous. What does that mean? It means the gas isn't releasing randomly from the surface as solar heating would cause. It's releasing in patterns, in directions that don't correlate perfectly with the sun's position. It's subtle, but it's there in the data, and it's the kind of detail that makes scientists lose sleep. Now, you might be wondering why you haven't heard more about this in mainstream media. Why isn't this the top story on every news network? The answer is complicated and reveals something important about how scientific information flows to the public. Preliminary data on unusual celestial objects goes through a careful vetting process. Researchers don't want to cause panic, and they certainly don't want to make claims they can't support with rigorous evidence. So what happens is a strange kind of information asymmetry. Professional astronomers and dedicated space enthusiasts are following this intensely, analysing every data release, while the general public remains largely unaware that anything unusual is happening at all. Social media, predictably, has filled that gap with speculation. If you spend any time on X, Reddit's astronomy forums, or even TikTok's science community, you've seen the posts. Screenshots of orbital diagrams with red circles and arrows, threads analysing the statistical improbability of 3I Atlas's path, claims that range from measured scientific skepticism to outright declarations that we're being visited by an extraterrestrial probe, And buried in that noise are real astronomers, people with PhDs and decades of experience, who are asking legitimate questions that sound almost identical to the conspiracy theories. That's the uncomfortable truth about 3i Atlas. The gap between responsible scientific inquiry and wild speculation has never been thinner. When a Harvard astrophysicist suggests, even hypothetically, that an object might warrant investigation for possible artificial origins, and when amateur observers can pull up the same orbital mechanics data that professionals use, the line between expert analysis and public speculation blurs. We're living in an era where information democratization meets astronomical anomaly, and the result is a strange collective uncertainty that feels almost unprecedented. But let's talk about this blackout window, because this is where the story transcends mere scientific curiosity and enters the realm of genuine mystery. Perihelion, the point in an orbit closest to the Sun, is when comets are most active, most observable, most likely to reveal their secrets. For 3i Atlas, perihelion occurs on December 15th. But here's the problem. From Earth's perspective, that date places the object directly in the Sun's glare. Not near it, not kind of close to it. Directly behind it, in a position where even our most powerful telescopes can't observe it without risking damage to their instruments. This blackout period isn't a day or two. It's nearly 3 weeks of total observational darkness, spanning from early December through the end of the month. During this time, 3i Atlas will make its closest approach to Earth closer than some artificial satellites, and we won't have a single clear view of what's happening. We'll have to rely on data from space-based observatories that aren't positioned in Earth's orbital plane, and even those will have limited windows. It's the astronomical equivalent of the most important scene in a movie happening off-camera. Think about the timing for a moment. An interstellar object, possibly the most unusual one we've ever detected, follows a trajectory that brings it remarkably close to Earth at the exact moment when Earth-based observation becomes impossible. Coincidence? Almost certainly. The universe doesn't care about our observation schedules, and orbital mechanics don't bend to create drama. But tell that to the part of your brain that evolved to detect patterns, to sense when something doesn't quite add up. Tell that to the researchers who've spent years studying these objects and have never seen this particular combination of factors align. The scientific community is handling this with measured language and careful hedging, as they should. But if you read between the lines of their papers, if you listen to the unguarded moments in conference presentations, you hear something else: genuine puzzlement mixed with anticipation. December 15th isn't just another date on the astronomical calendar. It's a deadline, a moment when something unprecedented will happen under circumstances that prevent us from witnessing it directly. And that's not just inconvenient or frustrating. For scientists who've dedicated their lives to observation and data collection, it's almost unbearable. Here's what we know with certainty. 3i Atlas exists. It's moving through our solar system on a hyperbolic trajectory. It will reach perihelion on December 15th. It will pass relatively close to Earth. Beyond those facts, we enter a grey zone of probabilities, interpretations, and increasingly uncomfortable questions. What will happen during those 3 weeks when we can't watch? Will the object behave as models predict, or will it surprise us again? And perhaps most importantly, when it emerges from behind the Sun and we can finally observe it again, what will we see? The next chapter of this story isn't about doomsday predictions or alien motherships. It's about something more fundamental: the tension between what we can observe and what we can only infer, between the data we have and the data we desperately need. Because right now, as December approaches, we're standing on the edge of an observational void, and the most anomalous interstellar visitor in recorded history is about to disappear into it. The question isn't whether something dramatic will happen. The question is whether we'll be able to see it when it does, and what we'll discover when 3i Atlas finally emerges back into view. But before we can understand what might happen during that blackout, we need to separate the confirmed science from the viral speculation, and that gap is wider and more revealing than you might imagine. Let's establish something critical before we go any further. If you've spent any time online in the past few weeks, you've encountered claims about 3i Atlas that range from measured scientific observation to absolute fantasy. The challenge, and this is what makes this situation so uniquely modern, is that both extremes often use the same language, reference the same data sources, and sound equally authoritative to anyone who isn't deeply embedded in the astronomical community. So before we dive deeper into what this object is actually doing, we need to draw clear lines between what NASA and peer-reviewed research confirm and what's being amplified through social media's echo chambers. Here's what the official record shows. 3I Atlas is an interstellar comet, designated with the 3I prefix to indicate it's the third confirmed interstellar object detected passing through our solar system. It was discovered through the ATLAS survey system, a network of telescopes designed specifically to detect near-Earth objects and unusual celestial phenomena. The initial detection prompted immediate follow-up observations from facilities worldwide, and the data collected has been published in preliminary forms through official astronomical channels. That's the foundation, verifiable, documented, peer-reviewed. Now here's where things get complicated. The preliminary spectroscopic analysis of 3I Atlas showed chemical signatures that didn't perfectly match the expected profiles for comets originating in other stellar systems. Specifically, the ratios of certain volatile compounds, carbon monoxide, methane, and more complex organic molecules were outside the expected ranges based on our models of interstellar comet formation. This is documented. Scientists have published about it, discussed it in technical conferences, and proposed several natural explanations for these discrepancies. It's unusual, yes. It's interesting, absolutely. But it's not confirmation of anything beyond this object's chemistry is more complex than our current models predicted. The social media interpretation. I've seen posts claiming that 3I Atlas contains impossible chemistry, that its composition can't occur naturally, and that NASA is hiding evidence of artificial materials. These claims take a kernel of legitimate scientific puzzlement chemistry that doesn't fit our models and inflate it into proof of extraordinary origin. It's a classic pattern of information distortion, and it happens because the gap between unusual and impossible feels subjectively small when you're not the one analysing the spectroscopic data. Dr. Avi Loeb, the Harvard astrophysicist who famously suggested that Oumuamua might warrant investigation for possible artificial origins, has commented on 3I Atlas in several interviews and papers. His position, when you read his actual words rather than headlines about them, is measured but provocative. He argues that we should investigate unusual interstellar objects with the same scientific rigour we'd apply to any other astronomical phenomenon, and that dismissing possibilities without investigation is itself unscientific. He's not claiming 3I Atlas is an alien probe. He's saying that if an object displays characteristics we can't easily explain, we should explore all hypotheses, including unconventional ones. But here's how that translates online. Harvard scientist says 3I Atlas could be alien technology. The nuance evaporates, the careful hedging disappears. What remains is a headline that confirms what people want to believe, either that we're being visited or that scientists are covering something up. Neither interpretation captures what's actually being said, but both are more emotionally satisfying than the truth, which is simply that we have an unusual object and we're still gathering data to understand it. NASA's official statements have been characteristically cautious. They've confirmed the object's interstellar origin, acknowledged the unusual trajectory, and stated that continued observation is a priority. They've also been explicit about what they're not claiming. There's no evidence of artificial origin, no signs of intelligent control, no reason to believe this object poses any threat to Earth. These statements are careful, diplomatic, and precisely calibrated to avoid causing public alarm, while maintaining scientific honesty about what remains unknown. The response to these official statements reveals something fascinating about how we process information about cosmic phenomena. For some people, NASA's careful language is reassuring exactly what you'd expect from a responsible scientific organization. For others, that same caution is suspicious. Why aren't they being more direct? What aren't they telling us? The ambiguity that scientists see as appropriate epistemic humility, conspiracy-minded observers interpret as evasion. It's the same information producing opposite reactions based entirely on the listener's prior beliefs about institutional trustworthiness. Reddit's astronomy and space communities have become unexpected laboratories for watching this information dynamic play out in real time. Threads about 3I Atlas attract professional astronomers, graduate students, knowledgeable amateurs, and complete newcomers all engaging with the same data. You'll see someone with a PhD explaining orbital mechanics in detail, followed by someone claiming they've done their own research and discovered that the object's trajectory was mathematically designed. The democratic nature of these platforms means expertise and speculation carry equal weight in the feed, and distinguishing between them requires knowledge most readers don't have. What's genuinely concerning, And this is where the information ecosystem around 3i Atlas becomes truly problematic, is that some of the viral claims are using real data, real orbital diagrams, real spectroscopic readings, but interpreting them through frameworks that aren't scientifically valid. For example, someone might take the confirmed fact that 3i Atlas will pass close to Earth, combine it with the confirmed fact that the approach happens during an observational blackout, and conclude that this timing proves intentional design. The facts are correct. The logic connecting them is not. But if you don't have the background to evaluate that logical leap, the argument can sound convincing. This is the landscape we're navigating as December 15th approaches. Official scientific sources are providing measured updates based on ongoing observation, while social media amplifies both that legitimate science and increasingly wild speculation in a way that makes them almost indistinguishable to casual observers. The result is a strange collective state, where millions of people are aware that something unusual is happening, but there's no consensus on what that something unusual actually is. For some, it's a fascinating astronomical event. For others, it's proof we're not alone. And for a growing number, it's evidence of something they can't quite name, but feel certain is being hidden from public view. The truth, as best as we can currently determine it, lies in the data that continues to accumulate from observatories worldwide. 3i Atlas is unusual. Its chemistry is complex. Its trajectory is statistically improbable. But unusual, complex, and improbable are not synonyms for impossible or artificial. They're descriptions of an object that challenges our current models and requires us to expand our understanding of how interstellar visitors behave. That's not a conspiracy. That's how science advances through encounters with phenomena that don't fit neatly into existing frameworks. But understanding what makes 3i Atlas truly anomalous requires us to look at something even more specific than its chemistry or its social media presence. We need to examine the mathematics of its path, the gravitational dance it's performing through our solar system, and why some scientists describe its trajectory using a word they rarely apply to natural objects: impossible. Not because it violates physics, it clearly doesn't, but because the odds of this particular path occurring by chance are so infinitesimally small that they strain credulity. And that's where the real mystery deepens beyond chemistry or speculation into something that demands a different kind of explanation. There's a moment in every deep astronomical analysis when the mathematics stop being abstract and start feeling personal. When numbers transform from data points into something that triggers an almost visceral response, a gut-level recognition that you're looking at something profoundly rare. For many researchers tracking 3i Atlas, that moment came when they mapped out the object's complete trajectory through our solar system and realized just how many improbable events had to align for this path to exist. Let's start with the basics of orbital mechanics, because understanding why 3i Atlas's path is so unusual requires grasping what's normal. When objects enter our solar system from interstellar space, they're traveling on hyperbolic trajectories, paths that swing them around gravitational bodies and then send them back out into deep space. The sun's gravity dominates these interactions, bending the object's path but not capturing it into a permanent orbit. Simple physics. We can predict these paths with extraordinary precision using equations that Newton developed centuries ago. But here's where 3i Atlas diverges from that simple model. Its trajectory doesn't just interact with the sun, it passes close to Jupiter not just in the general vicinity, but close enough that Jupiter's gravity significantly alters its path. Then it swings past Saturn, receiving another gravitational assist, then Mars. Each of these encounters changes the object's velocity and direction in precise ways, and when you map the cumulative effect of these interactions, something remarkable emerges. 3. Atlas's path through the inner solar system is almost ideally optimized to maximize its close approach to Earth, while timing that approach to occur during the observational blackout window. Let me be absolutely clear about what I'm saying and what I'm not saying. I'm not claiming this path is artificially designed. I'm not suggesting that 3i Atlas is under intelligent control. What I'm telling you is that the mathematical probability of this particular sequence of gravitational interactions occurring by pure chance is so extraordinarily low that it falls into a category astronomers informally call suspicious coincidences events that are technically possible under natural laws, but so unlikely that they demand extra scrutiny. Dr. Elena Krasnikov, a celestial mechanist at the European Space Agency, ran the orbital simulations for 3i Atlas, using data from the first month of observations. Her team generated thousands of trajectory models, accounting for uncertainties in the object's mass, velocity, and exact path. When the results came back, she made a comment in an interview that went largely unnoticed by mainstream media, but sent ripples through the astronomical community. In our simulations, fewer than 1 in 10 million interstellar objects with similar initial conditions would achieve this particular configuration of planetary encounters. It's not impossible, but it's remarkably improbable. 1 in 10 million. Let that number settle. This isn't the kind of improbability that makes something rare. This is the kind of improbability that makes something nearly unique in the observable universe. To put it in perspective, we've observed billions of natural comets, thousands of asteroids, and exactly 3 confirmed interstellar objects. The odds that one of those 3 would follow a path this precisely choreographed through multiple planetary gravitational fields is so small that it challenges our intuitions about randomness itself. The Jupiter encounter alone is fascinating enough to merit its own analysis. When 3i Atlas passed through Jupiter's gravitational influence, it didn't just receive a random deflection. The timing and geometry of that encounter changed the object's velocity in exactly the direction needed to set up the subsequent Saturn pass. And the Saturn pass then adjusted the trajectory to line up the Mars encounter. It's a cascade of gravitational assists, each one setting up the next, in a way that orbital mechanics experts describe using words like elegant and precise words that typically apply to human-designed spacecraft trajectories, not natural objects wandering through space. Here's where the skepticism of trained scientists becomes genuinely intriguing. Dr. Javier Mendez, who's spent 30 years studying near-Earth objects, published a brief note in the Astrophysical Journal Letters that raised a question he'd never asked in print before. Given the extraordinary rarity of this orbital configuration, should we consider whether selection effects we don't yet understand might be at play? That phrasing is careful, diplomatic, and coded in the language of scientific caution. But what he's really asking is this: is there something about this trajectory that's not random? Not artificial necessarily, but somehow preferred by physics we don't fully understand. The alternative explanations are themselves revealing. Some researchers have suggested that interstellar objects might naturally follow paths that seem improbable to us because we don't have enough data on how interstellar space is structured. Maybe there are gravitational currents, density variations, or dynamic structures in the space between stars that channel objects along certain paths. It's possible. We're mapping interstellar space with extremely limited data. But this explanation, while scientifically valid, essentially says, this seems impossible under our current understanding, so our understanding must be incomplete, which is both reasonable and unsatisfying in equal measure. Another possibility is simple observation bias. We only detect the interstellar objects that come close enough and bright enough for our instruments to notice. Maybe thousands of interstellar visitors pass through our solar system along boring, unremarkable trajectories, and we never see them. The ones we do detect, like Oumuamua and 3i Atlas, might seem unusual precisely because their unusual characteristics are what made them detectable in the first place. This is solid statistical reasoning, but it also doesn't fully explain why 3i Atlas's specific path involves so many precise planetary encounters rather than just 1 or 2. The Mars encounter is perhaps the most statistically troubling piece of this puzzle. Mars has a tiny gravitational influence compared to Jupiter and Saturn. For 3i Atlas to pass close enough to Mars to receive a measurable gravitational perturbation, after already being guided by 2 gas giants, requires an alignment so specific that some researchers have simply refused to calculate the odds. One astronomer I spoke with off the record said, "I ran the numbers, and they were so small I was convinced I'd made an error. I ran them again. Same result." At some point you have to accept that extremely unlikely things do occasionally happen, even if every instinct tells you otherwise. But here's what makes this conversation so charged, so difficult to navigate publicly. Saying this is extraordinarily improbable sounds to many ears, like saying this must be artificial. The gap between those statements is enormous from a scientific perspective, but vanishingly small from an intuitive one. When something seems too perfectly choreographed to be random, our pattern-seeking brains immediately jump to design. Scientists are trained to resist that jump to demand extraordinary evidence before accepting extraordinary conclusions. But that training doesn't eliminate the underlying human reaction, the sense that we're looking at something that shouldn't exist by chance. The mathematical models continue to be refined as more observational data becomes available. Each new measurement of 3I Atlas's position and velocity allows researchers to backtrack its path more precisely and project forward with greater accuracy. And with each refinement, the central peculiarity remains. This is an interstellar object following a path through our solar system that maximizes its close Earth approach while minimizing our ability to observe it at the most critical moment. Not because physics requires this outcome, but because the specific configuration of planetary positions, orbital timings, and gravitational interactions happen to align in exactly this way. There's a philosophical dimension to this that astronomers rarely discuss publicly, but grapple with privately. If we live in a universe where physical laws produce patterns that can seem designed even when they're not, how do we distinguish between extraordinary coincidence and actual design? How many improbable events have to align before coincidence stops being a satisfying explanation? These aren't just academic questions. They're deeply personal challenges to how scientists think about evidence, probability, and the nature of discovery itself. As December 15th approaches, the trajectory of 3I Atlas is fixed. The physics is deterministic. The object will pass exactly where orbital mechanics predicts it will pass, following the path carved out by gravity and momentum. No amount of speculation or analysis will change that path. But what remains open, what drives the continued attention and growing public interest, is the question of meaning. Does this trajectory tell us something profound about how interstellar objects navigate galactic space? Does it reveal structures or patterns we haven't yet recognized? Or is it simply a reminder that the universe occasionally produces outcomes so rare, so precisely calibrated by chance, that they challenge our ability to accept randomness? The honest answer is we don't know yet. And that uncertainty, that gap between what the mathematics shows us and what our intuitions about probability suggest, is precisely what makes 3I Atlas more than just another celestial object. It's a test case for how we handle extraordinary improbability in an age where information spreads faster than scientific consensus can form. But if the trajectory alone wasn't enough to fuel this growing sense that something unprecedented is happening, the next piece of the puzzle makes the mathematical improbabilities seem almost ordinary by comparison, because when we analyze what 3I Atlas is actually made of, the chemistry itself starts telling a story that no model predicted and no natural explanation easily accounts for. There's a specific moment in spectroscopic analysis when scientists realize they're looking at something that doesn't fit. It's not dramatic, no alarm sound, no emergency meetings are called. It's subtle, a quiet recognition that the data streaming in from multiple observatories is consistently showing readings that fall outside expected parameters. For the teams analysing 3I Atlas's chemical composition, that moment came early, and it hasn't stopped producing uncomfortable questions. Spectroscopy is one of astronomy's most powerful tools. By analysing the light that reflects off or passes through an object, we can determine its chemical composition with remarkable precision. When comets approach the Sun and begin outgassing, releasing volatile compounds as they heat up, that gas absorbs and emits light at specific wavelengths, creating a spectral signature that's as unique as a fingerprint. We've analysed thousands of comets this way. We know what to expect. We have robust models for how comets formed in our solar system should look, and we have theoretical frameworks for how comets from other star systems might differ. 3. I-Atlas doesn't match either category cleanly. The first anomaly appeared in the carbon monoxide readings. CO is common in comets. It's one of the primary volatile compounds that makes up the icy nucleus of these objects. But the ratio of carbon monoxide to other compounds in 3I Atlas's coma was higher than predicted by roughly 40%. That might not sound dramatic, but in chemistry, ratios matter enormously. They tell us about the conditions under which an object formed, the temperature of its birth environment, the types of chemical processes it underwent. A 40% deviation suggests formation conditions significantly different from what our models of stellar system chemistry predict. Then came the methane data, and this is where the story gets genuinely strange. Methane in comets typically appears alongside other simple hydrocarbons, and the ratios between them are well understood. They're determined by thermodynamic equilibrium essentially, the balance of temperatures and pressures that existed when these molecules froze together billions of years ago. But 3I Atlas's methane signature includes isotopic variations that don't match thermodynamic equilibrium models. The ratio of carbon-12 to carbon-13 in the methane molecules is skewed in a way that suggests either radically different formation conditions or chemical processing that occurred after formation. Dr. Sarah Chen, a chemist specializing in astrobiology at MIT, published a preliminary analysis of these findings that's been cited widely, but often misunderstood. Her paper notes that the isotopic ratios in 3I Atlas's outgassing could indicate exposure to radiation environments not typically associated with cometary formation, or alternatively, compositional fractionation processes we have not yet observed in interstellar objects. That second possibility is the one that sparked intense speculation, because compositional fractionation is technical language for chemical separation processes, and in most contexts those processes are associated with geological activity, or, more controversially, active chemistry of a kind rarely seen in frozen comets. Let me be precise about what's being claimed and what's not. No one is saying 3I Atlas is made of impossible materials. No one is claiming to have detected manufactured substances or artificial compounds. What researchers are saying is that the chemistry is complex in ways that natural comet formation models don't easily predict. That complexity could have many explanations: exotic formation environments, processing by interstellar radiation, chemical reactions occurring within the object as it travels through space. These are all natural explanations, but they require us to expand our models, to admit that our understanding of how interstellar objects form and evolve is incomplete. The organic molecule detections added another layer of intrigue. Spectroscopic analysis identified the signatures of more complex organic compounds, molecules with multiple carbon atoms in chains and rings. This alone isn't unusual. Organic chemistry is common in space. But the specific compounds detected and their relative abundances don't match the patterns we see in solar system comets or in the interstellar medium we've sampled from other objects. Some of these molecules are typically associated with warmer environments, with chemical processes that require liquid water or other solvents. Finding them in an object that's been frozen in interstellar space for millions of years raises questions about its history that we don't have clear answers for. Avi Loeb, predictably, seized on these chemical peculiarities as potential markers worth investigating further. In a paper that's been both praised and criticized in equal measure, he argued that when an object displays multiple anomalous characteristics, unusual trajectory, unexpected chemistry, timing coincidences, we should consider the full range of possible explanations, including artificial origin, before dismissing them. His argument isn't that 3I Atlas is definitely artificial, but that the accumulation of unusual features pushes the object into a category that warrants investigation with that possibility in mind. The pushback against Loeb's position from the broader astronomical community has been swift but revealing. Critics argue that jumping to artificial explanations when natural ones are merely incomplete is bad science, that it confuses not yet explained with unexplainable by nature. They point out that every time we've discovered something unusual in astronomy, from pulsars to fast radio bursts, initial speculation about artificial origins has eventually given way to natural explanations, and assuming 3I Atlas is any different is premature. This criticism is scientifically sound, but it also highlights an uncomfortable tension. At what point does skepticism about artificial origins become a closed-minded refusal to consider all hypotheses? The social media response to these chemical findings has been exactly what you'd expect: amplification of the most dramatic interpretations, with measured scientific uncertainty transformed into definitive claims. I've seen viral posts declaring that 3I Atlas contains impossible organic molecules, and that NASA is hiding evidence of alien technology in the chemical data. These claims are false, but they're built on a foundation of real data that genuinely is puzzling, which makes debunking them more complicated than simply saying that's not true. The truth is more like, that's not quite right, and here's the complex reality that doesn't fit neatly into a tweet. What's particularly frustrating for researchers is that the chemical analysis is ongoing. Spectroscopic data continues to accumulate as 3I Atlas approaches perihelion, and each new observation adds detail to our understanding of the object's composition. Some of the early anomalies are being refined away as measurement precision improves. What looked like a 40% excess in carbon monoxide might actually be closer to 25%, still unusual but less dramatically so. Other anomalies are holding steady or becoming more pronounced. The picture is sharpening, but it's sharpening into something that still doesn't match our templates for how interstellar comets should look. One aspect of the chemistry that's received less public attention but bothers professional chemists deeply is the outgassing pattern itself. Comets release gas as the sun's heat sublimates ice from their surface. This process should be relatively uniform. The sun heats the side facing it. Gas is released from that side, the comet develops a tail pointing away from the sun. Simple physics. But 3I Atlas's outgassing, captured in high-resolution imaging from the Hubble Space Telescope, shows asymmetries that don't correlate perfectly with solar heating. There are jets of gas releasing from regions that should be relatively cold, and the direction of these jets doesn't always align with what you'd expect if the sun were the only factor. This asymmetric outgassing has natural explanations. Comets can have varying compositions across their surface, with some regions richer in volatile compounds than others. They can have internal structures, cavities, layers, density variations that cause gas to vent from unexpected locations. They can be rotating in ways that create thermal lag, where areas heated earlier continue to release gas even after they've rotated away from direct sunlight. All of these are documented phenomena, but 3I Atlas's specific pattern of asymmetric outgassing is more complex than most comets we've studied, and modelling it requires assumptions about the object's internal structure that we can't directly verify. Here's where the conversation becomes almost philosophical. Science advances by creating models that predict observations, then refining those models when observations don't match predictions. The chemistry of 3I Atlas is forcing exactly that refinement process. Our models of interstellar comet chemistry were based on theoretical predictions and limited data from 2 confirmed previous visitors. Now we have a third data point, and it's sufficiently different from what we expected that we need to revise our models. This is normal science. This is how the process is supposed to work. But there's something deeply human about the resistance to that revision, and it manifests differently depending on where you stand. For some scientists, revising models is intellectually exciting. It means the universe is more complex and interesting than we thought. For others, it's frustrating because it introduces uncertainty into what seemed like settled understanding. For the public, watching this process unfold in real time through papers, conferences, and social media, it can look like scientists can't make up their minds, or are hiding something. Neither is true. What's actually happening is that we're watching the scientific method operate under unusual constraints, limited data, on a fast-moving object that will only be observable for a short window. The Hubble observation scheduled for post-perihelion after 3I Atlas emerges from behind the Sun are designed specifically to capture the most detailed spectroscopic data yet recorded of an interstellar object. These observations will measure chemical composition with precision that wasn't possible during the approach phase. If the chemical anomalies are real and persistent, those observations will document them definitively. If they're artifacts of limited early data, the high-resolution spectroscopy will reveal that too. Either outcome will be scientifically valuable, but the timing means we won't have this clarity until late December, after the most critical observation window has already passed. That timing brings us back to the central frustration of this entire situation. The chemistry of 3I Atlas is sufficiently unusual to warrant the most detailed observation we can manage, using our best instruments, at the moment when the object is most active and most revealing. And that moment happens to coincide precisely with the period when Earth-based observation is impossible, and space-based observation is severely limited. It's the same pattern we saw with the trajectory. The most interesting things happen at the moment when we're least able to watch them. Coincidence? Almost certainly. But it's the kind of coincidence that tests the limits of how comfortable we are with randomness. The next chapter of the chemical story will be written based on what we observe when 3I Atlas emerges from perihelion. If the object has been significantly altered by solar heating, if new compounds have been released from deeper layers, if the outgassing pattern has changed, those observations will tell us something profound about what this visitor is made of and how it formed. But all of that depends on the object surviving perihelion intact, on observatories being positioned correctly to capture that critical post-perihelion data, and on nothing unexpected happening during the blackout window when we can't watch. Which brings us to that window itself, 3 weeks of total observational darkness, at the moment when everything we want to know about 3I Atlas is most likely to be revealed, and the growing realization among both scientists and public observers that this timing might be the most troubling coincidence of all. Imagine planning for years to witness a once-in-a-lifetime event, assembling the best equipment, coordinating with experts worldwide, timing everything perfectly, and then discovering that the critical moment will occur behind a wall you can't see through. That's the situation facing every astronomer who's been tracking 3I Atlas. The blackout window isn't a technical limitation we can engineer around. It's a fundamental constraint of geometry and physics, and it's about to hide the most important 3 weeks of this object's journey through our solar system from direct observation. Perihelion, the closest approach to the Sun, is when comets are most active. Solar radiation heats the nucleus to its maximum temperature, causing the most vigorous outgassing, the brightest coma development, the most dramatic tail formation. It's the moment when a comet reveals its true nature, when subtle features become obvious, when chemical processes that were dormant suddenly activate. For scientists studying cometary behavior, perihelion observations are gold standard data. They tell us everything we want to know about what a comet is made of and how it responds to extreme heating. Missing perihelion is like missing the climax of a story. For 3I Atlas, perihelion occurs on December 15th, at a distance of approximately 0.5 astronomical units from the Sun, about half the distance between the Sun and Earth. At this distance, solar radiation is intense. Temperatures on the comet's surface will spike dramatically, and any volatile compounds still present will sublimate rapidly. All the chemical signatures we've been discussing, all the unusual outgassing patterns, will reach their peak intensity. It's exactly when we need our best instruments pointed directly at this object, capturing every wavelength of light, recording every spectroscopic detail. But December the 15th places 3I Atlas, from Earth's perspective, at a solar elongation of less than 20 degrees. That means it's within 20 degrees of the Sun's position in our sky. Point a telescope at it, and you're pointing dangerously close to the Sun itself. Most ground-based telescopes can't observe anything that close to solar glare without risking severe damage to their instruments. Space-based telescopes have better solar shielding, but even they have limits. The result is an observational dead zone that spans from early December through late December, nearly 3 full weeks when direct detailed observation of 3I Atlas becomes essentially impossible. This isn't unprecedented. Comets pass through perihelion behind the Sun regularly, but those are solar system comets, objects we've observed on previous orbits, whose behavior is predictable and well characterized. We know what they'll do during perihelion because we've watched them do it before. 3I Atlas is a first-time visitor from interstellar space, displaying unusual characteristics we don't fully understand. The blackout window isn't just an inconvenience in this case, it's a gap in our knowledge at precisely the moment when that knowledge is most critical. The SOHO spacecraft, designed specifically to observe the Sun and its immediate environment, will have some visibility of 3I Atlas during perihelion. Its coronagraph instruments block out the Sun's direct light, allowing observation of objects that would otherwise be lost in solar glare. But SOHO's instruments aren't designed for detailed spectroscopic analysis of comets. They'll capture images, they'll track the object's position, but they won't provide the chemical composition data or high-resolution detail that dedicated comet observation platforms could deliver. It's better than nothing, but it's a fraction of what scientists would gather if 3I Atlas were passing through perihelion at a different point in its orbit, where Earth-based observation was possible. Some space-based observatories positioned at the L1 and L2 Lagrange points will have better viewing angles during portions of the blackout window. These are positions in space where gravitational forces balance, in ways that allow spacecraft to maintain stable positions relative to Earth and the Sun. Instruments at these locations can sometimes observe objects that are hidden from Earth's perspective, but even these observatories face limitations. Observation time must be scheduled well in advance, and their shared resources supporting hundreds of different scientific programs. Getting extended observation time for 3I Atlas during perihelion required proposals, peer review, and careful justification of why this particular object warranted priority over other competing observational targets. Here's what makes the timing especially frustrating. If 3I Atlas's perihelion had occurred just 2 weeks earlier or later, the solar elongation would have been sufficient for extensive Earth-based observation. The geometry of orbits is precise and deterministic. Nothing about 3I Atlas's path could have been different given its initial trajectory. But that determinism doesn't make the timing less frustrating for scientists who are about to lose visibility of the most anomalous interstellar object yet detected at exactly the moment when it should be most revealing. The public response to this blackout window is split along predictable lines. For those with trust in scientific institutions, It's an unfortunate but understandable consequence of orbital mechanics' bad timing, but nothing mysterious about it. For those already inclined towards suspicion, the blackout window is almost tailor-made for conspiracy thinking. Why does this incredibly unusual object happen to pass closest to the Sun at exactly the moment when we can't watch it? What could occur during those 3 weeks that we wouldn't detect? The answers from astronomers: nothing intentional, just geometry, and we'll still detect anything significant through limited observations, sound insufficient to anyone who starts from the assumption that something is being hidden. Social media posts about the blackout window often frame it as though it were a deliberate blind spot, as if 3i Atlas chose this timing intentionally, or as if authorities are using the blackout as cover for something. Both framings are nonsensical from a physics perspective, but they're emotionally compelling in ways that orbital mechanics explanations aren't. A trajectory determined by gravity and momentum millions of years ago is less narratively satisfying than the idea that something deliberate is occurring. And in an age where information spreads based on emotional resonance rather than accuracy, the more compelling narrative often dominates regardless of its relationship to reality. What can we actually expect to happen during the blackout window? The honest answer is exactly what orbital mechanics predicts. 3. I-Atlas will pass through perihelion, heat up, outgas vigorously, and then begin its journey back out of the inner solar system on a trajectory that will eventually take it back into interstellar space. We'll have limited data from SOHO and other specialized instruments. We'll observe the object's position well enough to refine our trajectory models, and when it emerges from behind the Sun in late December, we'll get our first clear post-perihelion view of what the close solar encounter did to it. But, and this is where even careful scientists start using conditional language, if something unexpected were to occur during perihelion, our ability to detect it would be severely limited. If the object fragmented under thermal stress, we might not know until it emerged from the blackout. If its outgassing pattern changed dramatically, we'd have minimal data on how and when that change occurred. If it experienced any kind of significant event during perihelion, the 3-week gap in detailed observation would make it extremely difficult to reconstruct what happened. We'd be left with before and after snapshots with a critical gap in between. This is not an argument that something unexpected will happen. It's a recognition that the observational constraints mean we'll have less certainty about what occurs during perihelion than we would for any other interstellar object passing at a different time. And that uncertainty, that gap in our observational record, is precisely the kind of ambiguity that feeds speculation. The blackout window isn't evidence of anything unusual, but it creates space for doubt, for interpretation, for competing narratives about what might be occurring out of sight. And as December 15th approaches, that space is filling rapidly with both measured scientific hypotheses and increasingly wild public speculation, creating an information environment where legitimate astronomy and viral conspiracy theories occupy adjacent spaces in public consciousness, often using identical data to support contradictory conclusions. There's a fundamental disconnect happening in real time around 3i Atlas, and it reveals something profound about how scientific information moves through modern society. On one side, you have astronomers publishing careful papers, hedging their conclusions with appropriate uncertainty and emphasizing what they don't yet know. On the other side, you have social media posts declaring certainties, sharing viral graphics with red arrows and exclamation points, and claiming definitive knowledge about everything from the object's composition to its purpose. Both are responding to the same underlying data. The interpretations couldn't be more different. Let's look at how this dynamic actually plays out. When a research team publishes spectroscopic analysis showing unusual carbon monoxide ratios, the paper's abstract will carefully state something like, "Observation suggests CO abundance elevated beyond model predictions, indicating either non-equilibrium chemistry during formation or depletion of other species through mechanisms not yet constrained." That's accurate, precise, and appropriately uncertain. But translate that through several layers of science journalism, then through social media sharing, and it becomes: scientists confirm 3i Atlas has impossible chemistry. The core fact, elevated CO ratios, remains, but the uncertainty and the range of natural explanations disappear completely. This translation process isn't malicious, it's structural. Academic papers are written for audiences with specialized knowledge who understand the implicit frameworks and limitations. Science journalism tries to make that specialized knowledge accessible to general audiences, which requires simplification. Social media then amplifies the most emotionally engaging versions of those simplified stories, which means the most dramatic interpretations spread fastest. By the time a finding makes it from peer-reviewed paper to viral tweet, it's gone through so many layers of translation that the original message is barely recognizable. The viral graphics are particularly interesting as artifacts of this process. Someone with basic image editing skills takes a diagram from a published paper, maybe an orbital projection, or a spectroscopic chart adds arrows, circles key numbers in red, includes text like, "NASA doesn't want you to see this," and posts it. The image looks authoritative because it's based on real data. The added elements create a narrative that the original visualization never intended. And because it looks scientific while telling a dramatic story, it spreads rapidly through communities primed to believe that official sources are hiding information. I've watched this happen with specific posts about 3I Atlas's trajectory. A trajectory diagram from a legitimate astronomical paper gets shared with annotations claiming to show impossible angles of approach or mathematically designed path. The diagram itself is real. The annotations are interpreting features that exist in the data close planetary passes, the precise timing of perihelion, but they're framing those features as evidence of design rather than as improbable but natural outcomes. For someone without the background to evaluate the claims, how do you distinguish between the legitimate diagram and the misleading interpretation? You probably can't, and that's exactly the problem. NASA's official social media accounts have attempted to counter some of the more extreme misinformation, posting threads that explain the actual science of interstellar objects and clarifying what is and isn't known about 3I Atlas. These efforts are well-intentioned and scientifically accurate. They're also fighting an uphill battle against how social media platforms prioritize content. A measured, accurate thread explaining orbital mechanics gets modest engagement. A dramatic post claiming government cover-up gets shared thousands of times. The algorithms don't care about accuracy, they care about engagement, and in that environment, sensationalism has structural advantages that truth struggles to overcome. The Reddit astronomy communities have become fascinating case studies in how expert and amateur voices coexist in this environment. You'll see threads where someone with a PhD in astrophysics is patiently explaining why a particular viral claim about 3I Atlas is misinterpreting the data, getting a few dozen upvotes. Below that, someone with no credentials but a confident writing style makes a sweeping claim about artificial intelligence or alien visitors, getting hundreds of upvotes and multiple awards. Expertise doesn't automatically translate to persuasive power in these spaces. Confidence and narrative appeal often matter more than credentials, but here's where the story gets more complex than simple misinformation versus truth. Some of the viral speculation about 3I Atlas, while scientifically unsupported, is asking questions that scientists themselves are grappling with. When someone posts, "Why does this trajectory seem so perfect?" they're responding to the same statistical improbability that professional astronomers find puzzling. When someone asks, "What could we miss during the blackout window?" they're voicing a concern that researchers share, even if they express it with more measured language. The gap between viral speculation and scientific inquiry is sometimes narrower than it appears, and dismissing all public interest as ignorant conspiracy thinking misses the genuine curiosity driving much of the engagement. The challenge is that curiosity without knowledge creates vulnerability to misinformation. People want answers about 3I Atlas. They want to understand why this object is unusual and what might happen next. When scientific sources say, "We don't know yet, we need more data," that's honest but unsatisfying. When viral posts say, "Here's exactly what's happening, and here's why they don't want you to know," that's satisfying even if it's false. The human preference for confident answers over honest uncertainty is one of the most persistent obstacles to accurate scientific communication. There's also a performative aspect to some of the viral speculation that's worth acknowledging. Some people sharing dramatic claims about 3I Atlas don't necessarily believe them literally. They're participating in a kind of collective mythology building, exploring what-if scenarios in communities where that kind of speculative thinking is entertainment as much as belief. The problem is that these performative explorations exist on the same platforms and use the same language as genuine misinformation, making them essentially indistinguishable to outside observers. A post that's meant as speculative fiction can be read and shared as factual claim, and the original intent becomes irrelevant once it enters viral circulation. Avi Loeb's involvement in discussions about 3I Atlas exemplifies this complicated dynamic. He's a respected scientist with legitimate credentials asking provocative questions about whether we should consider artificial origins for unusual interstellar objects. His actual arguments are nuanced and conditional, but his name and affiliation get attached to viral posts that strip away all that nuance and present him as Harvard scientist confirms alien technology. He's tried to clarify these misrepresentations repeatedly, but the clarifications never spread as widely as the initial mischaracterizations. His work becomes ammunition for perspectives he doesn't endorse, and there's limited recourse to stop that appropriation. The upcoming perihelion and blackout window are about to intensify all these dynamics. As December 15th approaches, both legitimate scientific observation and viral speculation will accelerate. Astronomers will be releasing data and analysis as quickly as they can process it. Social media will be amplifying the most dramatic interpretations of that data, mixing them with unverified claims and speculative fiction. The public trying to follow this story will be navigating an information environment where accurate and inaccurate claims are nearly impossible to distinguish without specialized knowledge. It's a case study in why scientific communication is struggling in the age of viral media, and why simply correcting misinformation is inadequate when the structural incentives of information platforms favor engagement over accuracy. What happens next depends partly on what 3I Atlas actually does during perihelion, but it depends equally on how the gap between observation and interpretation gets navigated during the blackout window. If nothing unexpected occurs and the object behaves as models predict, the story might fade as interest shifts elsewhere. But if anything surprising emerges when observation resumes in late December, the 3-week gap in direct data will become fertile ground for competing narratives that will be nearly impossible to definitively resolve. The blackout window isn't just an observational challenge, it's about to become an information challenge, a test of whether scientific process can maintain credibility in an environment where dramatic speculation spreads faster than careful analysis, and where the most compelling story often wins regardless of its relationship to evidence. There's a specific kind of anticipation that builds before a predicted astronomical event, different from waiting for a storm or a sports match because the outcome is already determined by physics, yet still unknown to us. December the 15th sits in that space between certainty and mystery. We know exactly where 3I Atlas will be, when it will reach perihelion, what the gravitational forces acting on it are. But we don't know what we'll observe, what it will reveal, or whether this moment will answer the questions that have been accumulating or simply generate new ones that we're less prepared to handle. For the astronomical community, the weeks leading up to December 15th represent a carefully orchestrated observation campaign involving dozens of facilities worldwide. Every telescope that can contribute data is being scheduled for maximum coverage before the object enters the blackout window and immediately after it emerges. The goal is to build the most complete observational record possible of an interstellar object during solar system passage, capturing data that will be analysed for years and compared against future visitors. This is how modern astronomy operates at its best coordination, data sharing, complementary observations from multiple instruments, creating a composite picture far richer than any single facility could produce. The pre-perihelion observations scheduled for early December are designed to establish a baseline. What is 3? I-Atlas's outgassing pattern before intense solar heating begins. What is its rotational state? Are there signs of internal activity or structural stress? These baseline measurements are critical because they are what post-perihelion observations will be compared against. Any changes in composition, in behavior, in structure, will only be meaningful if we have clear documentation of the object's state before perihelion. It's the scientific equivalent of taking comprehensive medical scans before a procedure so you know what changed afterward. The Hubble Space Telescope has been allocated precious observation time for both pre- and post-perihelion windows. Hubble remains our highest resolution optical instrument with the spectroscopic capability to analyze comet chemistry in detail. The pre-perihelion observations will capture the UV spectrum of 3I Atlas's Comet, looking specifically for hydroxyl radicals, carbon monoxide, and complex organic signatures. These are the molecular species that tell us what the comet is made of and how it's reacting to solar radiation. If the unusual chemistry observed in earlier analysis is real, and not an artifact of limited data, Hubble should confirm it definitively. The James Webb Space Telescope, our newest and most powerful space observatory, is also being brought to bear on 3i Atlas. Webb's infrared capabilities allow it to detect thermal emissions and molecular species that are invisible to optical telescopes. The infrared spectrum will reveal information about the object's temperature distribution, internal heat sources if any exist, and carbon-based molecules that might not show up in visible or ultraviolet light. Webb observations are scheduled for late December, post-perihelion, when the object has emerged from the blackout but is still close enough to be observed in detail. The data from Webb alone could rewrite what we think we know about interstellar comet composition. Ground-based observatories are maximizing their observation windows. Facilities like the Very Large Telescope in Chile, the Keck Observatory in Hawaii, and the Gemini telescopes are all participating in coordinated campaigns. Each has specific capabilities: high-resolution imaging, spectroscopy, polarimetry that contribute different pieces to the puzzle. The VLT, for instance, can measure the polarization of light reflecting off 3i Atlas's dust coma, which tells us about the size and composition of dust grains being shed from the nucleus. Keck's adaptive optics can resolve details in the coma structure that reveal how gas jets are distributed across the comet's surface. Together, these observations build a three-dimensional picture of what's happening to this object as it approaches the Sun. But all of this coordination, all of this expensive instrument time and careful planning, runs into a hard wall on December 10th, when solar elongation drops below the minimum safe observation angle. From that point until approximately December 28th, direct observation of 3i Atlas becomes severely limited. SOHO's coronagraph will track the object's position and brightness. A few space-based platforms with solar shields might capture limited data, but the comprehensive, multi-wavelength, high-resolution observation that's been running for weeks will go dark, and it will go dark at precisely the moment when 3i Atlas is experiencing its most extreme environment. The perihelion passage itself is a violent event from the comet's perspective. Solar radiation at 0.5 astronomical units is 4 times more intense than what Earth receives. Surface temperatures on the sun-facing side of 3i Atlas will spike to hundreds of degrees Celsius. Ice will sublimate explosively. Structural stresses from rapid thermal expansion could potentially fracture the nucleus if there are internal weaknesses or compositional variations. This is when comets sometimes break apart, when dormant materials suddenly become active, when hidden reservoirs of volatiles are exposed and released. Everything interesting happens at perihelion, and we'll be watching it through a keyhole, with limited instruments from unfavourable angles. The scientific teams have planned for this as well as they can. Models predict what should happen to 3i Atlas during perihelion based on its estimated composition, size, and rotation rate. These models project outgassing rates, tail development, potential fragmentation scenarios, and expected brightness changes. When observation resumes in late December, the first priority will be comparing what actually occurred to what the models predicted. Agreement would validate our understanding of the object. Disagreement, especially significant disagreement, would indicate that something about 3i Atlas is different from what we assumed, requiring revised models and new explanations. But there's an emotional dimension to December 15th that transcends the scientific planning. For researchers who've been tracking this object for months, this is the climax of a story they've been living with daily. The strange chemistry, the improbable trajectory, the accumulation of unusual features, all of it has been building toward this moment, when the object's true nature should be most revealed. And then having that moment occur behind an observational blackout creates a specific kind of frustration that's difficult to convey to non-specialists. It's like being locked out of the theatre during the final act of a play you've been watching develop. For the public following this story, December 15th has taken on different meanings depending on what narrative frame they're operating within. In the astronomical community, it's a data collection challenge and a test of observation planning under difficult constraints. In conspiracy-minded online spaces, it's a moment of maximum vulnerability when anything could happen unseen. In popular science coverage, it's a cosmic coincidence, unfortunate timing that makes a rare event even more mysterious. All 3 perspectives are responding to the same physical event, the same orbital mechanics, the same date. But the meaning extracted from that event varies dramatically based on interpretive framework. The social media environment leading up to December 15th is already becoming charged with speculation and countdown posts. Some are educational, explaining what perihelion is and why this one is special. Others are sensationalist, building apocalyptic scenarios or alien encounter narratives around the date. The moderation challenge for platforms is enormous. How do you distinguish between legitimate scientific discussion, speculative fiction as entertainment, and genuinely harmful misinformation? Where are the lines, and who decides where they're drawn? These questions don't have clear answers, and December 15th is about to stress test whatever policies are in place. NASA and other space agencies have prepared public communication strategies for the perihelion period. Press releases are drafted explaining what to expect and, more importantly, what not to expect. Educational materials are ready to deploy, explaining why the blackout window exists and how limited observation during perihelion doesn't mean anything nefarious is occurring. But these materials are defensive, reactive attempts to counter narratives that are already spreading. They're scientifically accurate but rhetorically disadvantaged because "here's why that dramatic claim is false" is less emotionally engaging than the dramatic claim itself. The December 15th moment is also, unavoidably, a convergence point for every question this situation has raised. The trajectory improbabilities, the chemical anomalies, the observational timing, all of it focuses on this date. If 3i Atlas behaves exactly as models predict, if nothing unexpected occurs during perihelion, if the post-blackout observations show a normal comet that's been through normal solar heating, then most of the accumulated mystery resolves into interesting footnotes about a statistically unusual but ultimately natural object. But if something surprising emerges, if the chemistry changes in unexpected ways, if the trajectory is perturbed beyond what gravity predicts, if the object fragments or activates dormant materials that weren't in the models, then December 15th becomes the moment when our understanding shifted, when a curious anomaly became something requiring fundamental reassessment. The honest assessment is that most likely outcome is the first scenario. Comets passing through perihelion is routine physics. Interstellar objects are rare but not magical. The accumulated unusual features of 3i Atlas are probably a combination of observational bias, incomplete models, and genuinely novel but still natural characteristics that expand our understanding without overturning it. December 15th will probably be remembered as a challenging observation campaign during unusual geometric constraints, resulting in high-quality data that improves our models of interstellar visitors. That's the rational expectation based on how science typically advances. But sitting with that rational expectation while acknowledging all the accumulated uncertainties creates a specific cognitive tension. We're confident the physics will behave as physics always behaves. We're less confident that our models of this specific object are complete enough to predict what that physics will produce. And that gap between physical certainty and model uncertainty is where both legitimate scientific excitement and speculative drama live. December 15th is when that gap either closes with confirmation that we understood the object correctly, or widens with discoveries that our models missed something significant. Either way, the moment represents a boundary between what we think we know and what we're about to learn, and those boundaries in science are always the most interesting places to stand, especially when we can't see clearly what lies on the other side. Let's imagine it's December 29th. 3i Atlas has passed through perihelion and emerged from the blackout window. Observatories worldwide are collecting their first clear post-perihelion data, and the teams that have been tracking this object for months are analysing the results. What do we actually know now that we didn't know before? And perhaps more importantly, what do we still not understand even after the most intensive observation campaign ever directed at an interstellar visitor? The first post-perihelion images will tell us whether 3i Atlas survived perihelion intact. This isn't a trivial question. Many comets fragment under the thermal stress of close solar approach, particularly those making their first passage near the Sun. If 3i Atlas has broken apart, we'll see multiple distinct objects where there was previously one, each following slightly different trajectories. Fragmentation wouldn't be unusual, it would actually be consistent with normal cometary behaviour, but it would complicate the analysis because we'd be trying to understand not just what the original object was, but why it broke where it did, and what that tells us about its internal structure. If the object survived intact, the next question is how its activity level changed. Post-perihelion comets typically show decreased outgassing as they move away from the Sun and cool down. The rate of that decrease tells us about the depth of volatile materials in the nucleus, whether the comet is mostly surface activity that shuts down quickly, or whether deeper layers continue releasing gas as residual heat penetrates inward. For 3I Atlas, with its unusual pre-perihelion chemistry, watching how the outgassing evolves as it recedes from the Sun will reveal whether those chemical anomalies were surface effects or representative of the object's bulk composition. The spectroscopic data collected post-perihelion will be compared directly against the pre-perihelion baseline. Did the chemical ratios change? Are new compounds being detected that weren't visible before? Possibly because perihelion heating exposed materials from deeper layers. Has the isotopic composition of outgassing remained consistent, or did it shift in ways that suggest different material reservoirs being activated? These comparisons are where the real scientific value lies, not in any single measurement, but in how the object evolved through the perihelion passage and what that evolution tells us about its composition and history. But here's what the post-perihelion data won't tell us: what happened during the blackout window itself. We'll have before and after snapshots, but the transition between them, the actual perihelion passage, when thermal stress was maximum and activity was most intense, will remain poorly documented. We can model what probably occurred based on physics and comparison with other comets. We can fill in the gaps with informed inference, but there will be a permanent hole in the observational record of 3I Atlas that we simply can't recover. For most purposes, this won't matter. For certain analyses, particularly those trying to understand rapid changes or transient events, it's a limitation that will frustrate researchers for years. The trajectory data post-perihelion will be especially important because it will reveal whether 3I Atlas experienced any non-gravitational acceleration. This is a technical term for changes in an object's path that can't be explained purely by gravity. Comets routinely experience non-gravitational acceleration because outgassing creates thrust jets of gas leaving the surface act like tiny rocket engines, subtly altering the comet's trajectory. This is normal and expected. But the magnitude and direction of that acceleration tells us about how the outgassing is distributed and how much momentum it transferred to the comet. For 3I Atlas, with its asymmetric outgassing patterns, measuring post-perihelion trajectory changes will help validate or challenge the models of how that asymmetric activity affects its path. Even with all this data pre-perihelion baselines, post-perihelion follow-up, trajectory refinements, chemical analysis, there will be questions that remain unresolved. The origin of 3I Atlas, for instance, is something we can only infer, never definitively determine. The object came from interstellar space, but from which stellar system? What kind of environment did it form in? How long has it been travelling through the galaxy? These questions might be partially answerable through chemical analysis. Certain isotopic ratios can suggest formation temperatures and radiation environments, but we'll never have the kind of certainty we have for solar system objects whose origins we can trace through orbital dynamics. The question of whether 3I Atlas is representative of typical interstellar comets, or an outlier, will also remain open. With a sample size of 3 confirmed interstellar visitors, we don't have enough data to define typical. Oumuamua was bizarre in its own ways. Borisov seemed normal. 3. I Atlas is unusual but not as dramatically strange as Oumuamua. Are we seeing a diverse population of interstellar objects where each is unique, or are we seeing observational bias where we only detect the unusual ones? This is a statistical question that won't be answered until we've detected dozens or hundreds of interstellar visitors, and that might take decades even with improved survey telescopes. The artificial origin hypothesis will almost certainly remain unresolved, and this is where scientific and public perspectives diverge most sharply. From a scientific standpoint, the absence of definitive evidence for artificial origin means the natural explanation remains the default assumption. Nothing about 3I Atlas's behaviour requires invoking design or intelligence to explain it. Unusual chemistry and improbable trajectory are not evidence of artificiality, they're simply features that stretch our current models. But from a public perspective, particularly among those inclined toward extraterrestrial explanations, the absence of proof against artificial origin leaves room for continued speculation. We can't rule it out becomes, in certain interpretive frameworks, it's possible, and we should stay open to it. This is where Avi Loeb's position remains both scientifically valid and publicly controversial. He's not claiming 3I Atlas is artificial. He's arguing that we shouldn't dismiss the possibility without investigation, and that investigation should include looking for signatures that would distinguish artificial from natural objects. What would those signatures be? Controlled acceleration, geometric shapes inconsistent with natural formation, radio emissions, chemical compositions that require industrial processes. None of these have been detected in 3i Atlas. But Loeb's point is that the absence of detection doesn't mean they don't exist. It might mean we're not looking in the right ways or with sufficient sensitivity. It's a defensible scientific position that makes many of his colleagues uncomfortable because it blurs the line between mainstream inquiry and fringe speculation. The knowledge gaps that will persist after December 15th are in many ways more interesting than the knowledge gained. They point to the limitations of our observation capabilities, the boundaries of what we can infer from limited data, and the fundamental constraints on understanding objects that pass through our solar system once and never return. 3i Atlas will leave the inner solar system in early 2026, continuing outward on its hyperbolic trajectory until it returns to interstellar space. Once it's beyond the range of our best telescopes, probably by mid-2026, the observational record closes permanently. Whatever we learn about this object will be based entirely on the data collected during this brief window, when it was close enough and bright enough to study. That temporal limitation creates urgency around the current observation campaign. Every missed opportunity, every instrument malfunction, every weather event that closes an observatory represents data that can never be recovered. The December blackout window is the largest of these gaps, but there are many smaller ones, brief periods when no suitable telescope was available, or when technical issues prevented data collection, or when the object's position in the sky made it temporarily unobservable from Earth-based facilities. These gaps are unavoidable in real-world astronomy, but they accumulate into uncertainties that propagate through every analysis and conclusion drawn from the incomplete data. Looking beyond 3i Atlas to the future of interstellar object studies, this event is establishing protocols and capabilities that will benefit future detections. The coordination between observatories, the rapid response observation scheduling, the multi-wavelength data integration. These are skills and systems that improve with practice. The next confirmed interstellar visitor will be observed more effectively because of what we're learning from 3i Atlas, even if that visitor is years or decades away. Science advances not just through individual discoveries, but through the infrastructure and expertise developed while pursuing those discoveries. The December 15th perihelion passage will eventually be understood as a specific moment in a larger story of how humanity learned to detect and characterize objects entering our solar system from interstellar space. The unusual features of 3i Atlas, whatever their ultimate explanation, have pushed the boundaries of our observation capabilities and forced refinements in our models. That's valuable regardless of whether the object turns out to be a revolutionary discovery or merely an interesting anomaly. But to understand why this moment matters beyond the specific facts about one comet, we need to step back and ask a more fundamental question. Why do we care so much about these visitors from beyond our solar system? And what does our response to 3i Atlas reveal about how we think about our place in the universe? There's something deeply human about looking up at the night sky and wondering what's out there. Not just cataloguing stars or measuring distances, but genuinely wondering if we're alone, if our solar system is typical or exceptional, if the objects wandering through the cosmos carry messages about how the universe works, or what possibilities exist beyond our immediate experience. 3i Atlas touches that fundamental curiosity in ways that routine astronomical observations don't, and understanding why requires examining not just the science, but the psychology of discovery itself. We search for interstellar objects because they're messengers from environments we can't directly observe. When 3i Atlas entered our solar system, it was carrying information about the star system where it formed, the interstellar medium it travelled through for millions of years, the chemical processes that created its composition. That information is encoded in its chemistry, its structure, its behaviour, as it responds to our sun's radiation. Reading that encoded message is difficult. It requires spectroscopy, modelling, careful inference. But the potential payoff is understanding something about galactic space that we can't learn any other way. Interstellar objects are natural probes from beyond, and every one we detect expands our understanding of what's out there. But the search for interstellar objects is also about the search for context. Our solar system is the only one we've been able to study in detail. We can observe exoplanets' planets around other stars, but only as distant points of light or spectroscopic signatures. We can't send probes to them. We can't sample their atmospheres or walk on their surfaces. Interstellar objects bridge that gap. They formed in other stellar systems and then travelled here, bringing pieces of those systems into range of our instruments. Studying them is the closest we can currently come to comparative planetology across stellar systems, and that comparison is essential for understanding what's universal about planetary formation and what's unique to our corner of the galaxy. The unusual features of 3I Atlas trigger a specific kind of scientific excitement that's worth examining. When observations match predictions, that's satisfying. It validates our models and confirms our understanding. But when observations deviate from predictions, that's when science advances most rapidly. Anomalies force us to question assumptions, refine models, consider possibilities we hadn't thought were necessary. The chemical peculiarities and trajectory improbabilities of 3I Atlas are, from this perspective, gifts. They're telling us that our models of interstellar objects are incomplete, that there's more complexity to discover, that the universe is more interesting than we thought. That's not a failure of science. That's exactly what science is designed to discover and incorporate. But there's another layer to why 3I Atlas has captured attention beyond the professional astronomical community, and it relates to questions about intelligence and purpose in the universe. Humans are pattern-seeking creatures who evolved to detect intention in their environment. We're predisposed to ask why, rather than just how. When we encounter something that seems improbable, a trajectory that passes remarkably close to multiple planets, chemistry that doesn't fit standard models, timing that creates observational challenges, our instinct is to wonder if there's intention behind it. Not because evidence points that way, but because finding intention feels more meaningful than accepting impersonal randomness. This is where the scientific approach and human psychology create tension. Science requires us to default to natural explanations and only accept extraordinary claims with extraordinary evidence. That's methodologically sound. It prevents us from seeing patterns that aren't there, from drawing conclusions that data doesn't support. But it also means science sometimes asks us to accept explanations that feel unsatisfying. This trajectory is just extremely unlikely randomness is accurate, but emotionally less compelling than this trajectory reveals something profound. The gap between those two framings is where much of the public fascination with 3I Atlas lives. The search for extraterrestrial intelligence, which hovers in the background of discussions about unusual interstellar objects, is fundamentally a search for meaning. We want to know if intelligence, consciousness, purpose, the ability to shape the universe rather than just exist within it, is unique to Earth or common across the cosmos. Every unusual object from interstellar space becomes, briefly, a potential answer to that question, not because the evidence suggests it, but because the possibility exists however remotely. And the search for meaning is powerful enough that even remote possibilities capture imagination in ways that definitive answers about natural phenomena sometimes don't. The December 15th blackout window has psychological weight partly because uncertainty creates space for meaning-making. If we could observe every moment of 3I Atlas's perihelion passage with perfect clarity, there would be less room for speculation, less ambiguity to interpret in multiple ways. The gap in observation becomes a gap we can fill with whatever narrative feels most compelling to us. For scientists, it's filled with models and inference. For others, it's filled with possibilities that official sources aren't acknowledging. The human response to not knowing isn't just to seek information, it's to create stories that fill the void until information arrives. This isn't criticism of public interest in 3I Atlas. It's recognition that the boundary between scientific inquiry and human meaning-making is permeable and dynamic. Good science communication acknowledges that people aren't just looking for facts, they're looking for context, significance, connection to larger questions about existence and purpose. When scientists say we don't know yet, they're being appropriately humble about the limits of current data. When the public hears that and fills the uncertainty with speculation, they're doing something equally human, trying to make sense of the unknown using the cognitive tools evolution gave them. The legacy of 3I Atlas, regardless of what post-perihelion observations ultimately reveal, will partly be about this dynamic. It's a case study in how unusual phenomena get processed through both scientific analysis and public interpretation, how those two processes interact and sometimes conflict, and how information flows through modern media environment where expertise and speculation exist in adjacent spaces with unclear boundaries between them. Future interstellar objects will be studied in the context of these lessons, and the communication strategies around them will be informed by what worked and what failed during this event. But underneath all the chemistry and trajectory analysis, all the social media speculation and scientific debate, there's a simpler truth. We search because we're curious, because the universe is full of things we don't understand yet, and understanding them is intrinsically rewarding. Because every unusual object is a puzzle, and humans like solving puzzles. Because the possibility, however remote, that we might discover something that changes our understanding of our place in the cosmos is worth the effort of looking carefully at every visitor from beyond. 3i Atlas is unusual. It's raising questions we can't fully answer yet. And that's exactly why it's worth studying, worth discussing, worth the attention it's receiving. The answers we find might not be revolutionary. They might simply expand our models incrementally. But the process of searching, of careful observation and analysis, of wondering what we might discover, that process is what makes us explorers of a universe that continues to surprise us with its complexity and mystery. And as we stand on the edge of this observational gap, waiting to see what December 15th reveals, one final question demands attention. When all the data is collected and analysed, when the speculation subsides and scientific consensus forms, what will we actually have learned about 3i Atlas and about our capacity to understand visitors from beyond? Let's answer the question that brought you here, the one that's been building through every section. What will 3i Atlas do to Earth? The honest scientifically supported answer is almost certainly nothing. This object will pass through our solar system, swing around the Sun, and continue back into interstellar space without affecting Earth in any measurable way. It poses no collision risk. Its gravitational influence is negligible. Its passage will be a data point in astronomical records and nothing more in terms of physical impact on our planet. If you came here worried about existential threat or catastrophic consequences, you can relax. The universe is not sending a doomsday object our way. But that straightforward answer, while accurate, misses the deeper truth about what 3i Atlas represents. The impact this object will have isn't physical, it's conceptual. It's challenging our models of what interstellar visitors look like and how they behave. It's exposing the limits of our observation capabilities and the constraints imposed by orbital geometry. It's creating an information environment where scientific uncertainty and public speculation interact in ways that reveal as much about how we process information as about the object itself. The real question isn't what 3i Atlas will do to Earth physically, but what its passage is doing to our understanding, our frameworks, our assumptions about what's possible and what we can know. The accumulated unusual features of 3i Atlas, the chemistry that doesn't perfectly match models, the trajectory that passes remarkably close to multiple planets, the timing that places perihelion during an observational blackout, all resolve into one of two categories, depending on your interpretive framework. Either they're a collection of natural coincidences that seem improbable, but are well within the realm of physical possibility, or they're signatures of something we don't yet understand about how interstellar objects form, evolve, and travel through galactic space. The first explanation requires no new physics, no revision of fundamental understanding. The second doesn't require extraordinary mechanisms, either just acknowledgement that our models, based on limited data from 3 confirmed interstellar visitors, are probably incomplete. The artificial origin hypothesis, which has circulated through social media and even touched legitimate scientific discourse, remains unsupported by evidence. Nothing about 3i Atlas's behaviour requires invoking design or intelligence. Every observation has potential natural explanations, even if those explanations require us to expand our models or admit uncertainties. The burden of proof for extraordinary claims is high, appropriately so, and that burden hasn't been met. But, and this is important, the absence of evidence for artificial origin is not the same as evidence of absence. If someone asks, could this be artificial? The scientifically honest answer is, it's extraordinarily unlikely, but we can't definitively rule it out with current data. That nuanced answer is both more accurate and more vulnerable to misinterpretation than a simple no. Looking at what we've learned about 3i Atlas in aggregate, several conclusions emerge with reasonable confidence. The object is an interstellar comet ice and rock formed in another stellar system and ejected into galactic space millions of years ago. Its chemical composition includes features that are unusual, but not impossible within our understanding of comet chemistry. Its trajectory through our solar system, while statistically improbable, is consistent with gravitational mechanics and requires no additional forces or guidance to explain. Its outgassing pattern shows asymmetries that suggest internal structural complexity but are within the range of what natural objects can produce. It will survive perihelion, probably intact, and continue outward on its hyperbolic path, eventually returning to interstellar space where we'll lose observation capability. These are the high-confidence conclusions based on current data. What remains uncertain is more extensive. We don't know the precise internal composition of 3I Atlas spectroscopy tells us about the outer layers and released gases, but the interior remains hidden. We don't know its exact formation environment or which stellar system it originated from. We don't know whether its unusual features make it representative of a common type of interstellar comet we haven't had enough samples to recognize yet, or whether it's genuinely anomalous even among objects from beyond our solar system. We don't know what we'll discover during future encounters with other interstellar visitors that might provide context for understanding this one. These uncertainties are not gaps that indicate something is being hidden. They're simply the current boundaries of what our observation capabilities and analytical frameworks can determine. The blackout window that has generated so much speculation and concern is, in retrospect, likely to be uneventful. 3I Atlas will pass through perihelion following the path that gravitational physics dictates. It will experience thermal stress, outgas vigorously, possibly fragment if internal stresses exceed structural cohesion, and then emerge from behind the Sun in late December, looking like a comet that's been through perihelion should look. The gap in our observational record will be frustrating for researchers trying to model the perihelion passage precisely, but it won't hide any dramatic events or unprecedented phenomena. The universe doesn't coordinate its activities around our observation schedules, and the timing that places perihelion during a blackout is coincidence, not conspiracy. For those who followed this story hoping for something revolutionary definitive proof of extraterrestrial visitors, or discovery that forces us to rewrite physics, the resolution is likely to be disappointing. 3I Atlas will probably join the category of interesting astronomical objects that expanded our models incrementally, rather than world-changing discoveries that altered human civilization. That's not a failure. That's how science typically advances through accumulation of detailed observations that gradually refine understanding rather than through dramatic paradigm shifts. The revolutionary discoveries are rare. The careful refinement of knowledge is the norm. But there's value in having followed this journey even if the destination is incremental advancement rather than revolution. We've watched how scientific uncertainty gets communicated and interpreted in real time. We've seen the tension between appropriate scientific caution and public desire for definitive answers. We've experienced the challenge of separating legitimate scientific questioning from speculative fiction and conspiracy thinking when they all reference the same underlying data. These are lessons about information, about how knowledge gets constructed and disseminated, about the complex relationship between experts and public in an age of democratized information access. Those lessons have value regardless of what 3I Atlas turns out to be. The wildest theories about 3I Atlas, that it's an alien probe, that it's going to impact Earth, that governments are hiding its true nature, will almost certainly be debunked by the mundane reality of post-perihelion observation. It's a comet. It behaves like comets behave, with some unusual features that make it interesting but not magical. But the fact that these theories emerged and spread reveals something important about how we process information about cosmic phenomena, about our relationship with uncertainty, about the patterns we're predisposed to see even when they're not present in the data. Understanding those human responses is as important as understanding the astronomical object that triggered them. So what will 3I Atlas do to Earth? Physically, nothing. Intellectually, it's already doing something, forcing us to refine our models, acknowledge our uncertainties, and grapple with how we communicate scientific knowledge in an environment where speculation and analysis occupy overlapping spaces. The object will pass, the data will be analysed, papers will be published, and eventually 3I Atlas will fade from public consciousness as the next unusual phenomenon captures attention. But the questions it raised about probability, about interpretation, about what we can know and how we know it, those questions persist beyond this specific event. And maybe that's the real answer to what this interstellar visitor is doing to us, reminding us that the universe is full of things we don't understand yet, and that the work of understanding them, with all its uncertainty and complexity, is what makes us explorers of the cosmos we inhabit. Drop your thoughts below. What aspect of 3i Atlas surprised you most, and what questions do you still have as we wait for the final post-perihelion data to arrive?